Okay, so the plan today is to go through the reinforce code implementation of the reinforce algorithm on the CartPole environment, OpenAI Gym's CartPole environment. But before we go through the code, let's do a quick overview of the lesson on policy gradient methods. So you will understand what's going on, what the reinforced algorithm is, and in case you haven't already gone through the lesson, this overview is going to be useful for you as well. Okay, so policy gradient methods. So what are policy gradient methods? Policy gradient methods are a subset of the policy-based methods that we saw last week. Now, policy-based methods are uh, opposite or are different than value-based methods. Policy-based methods directly look for optimal policy instead of going through the intermediate step of computing a value function. So policy-based method directly compute for optimal policy, that is the theta parameters of the network. And uh, we saw last week that we we make we have a theta and we have expected return u, and then we add some random noise to theta, and u will change, and then we add more random noise to theta and u will either increase or decrease. And then if u increases, that means the direction of the noise that we added is correct, so we add even more noise to theta. And if after this change u decreases, we uh, add noise to theta in another direction. So the policy-based method was a black box optimization method where we don't know the relationship between u and theta, and we just change theta and see how u is changing. And our objective there was to get a theta or the network parameters in such a way that u is maximum. U is the expected return. Okay. If you guys want more information on this, please check out my last week's webinar on policy-based methods. More details over there. So what is policy gradient methods then? So in this, as compared to policy gradient methods uh, also tries to look for best weights, best parameters to optimize u, that is the expected return. But in this case, we compute gradient of the expected return with respect to the parameters, and it's called gradient ascent because um, if u, the expected return, is increasing if we change theta in certain way, then we want to add that change to theta. This is the opposite to gradient descent, and this has been already discussed in last week's webinar, gradient ascent versus gradient descent. So please check that out. So uh, the improvement, rather than saying difference, the improvement in policy gradient method is that instead of randomly changing theta and trying to improve the expected return, we compute gradient, we compute the derivative of the expected return with respect to each of the parameters, and then we see how do we want to improve the parameters. Okay, so this is an example from the lesson. There is this bird or a chicken, and it wants to cross this road and reach here, and it has these 4 actions: up, down, left, right, and it wants to reach here. This is the objective. And so if we use policy-based methods, we will have a neural network and this will be the state. So if we are using CNN, convolutional neural networks, we will use the image of the state, and which will be fed to the neural network. If we are using if we don't have image as the input, we just have an array of the state parameters, then we don't use convolutional neural networks, we just use the linear layers, fully connected layers. So in this case, we have this image of the state. So this is what the bird is seeing right now, and it has to decide whether to go up, down, left, or right. So the bird, sorry, the chicken, whatever, has the agent has this network. It feeds. It looks at this image. It feeds it to its network, and its network will give out probabilities of taking each action, right? And based on this and its policy, whether the bird wants to sample one of these probabilities or want to go with the action that has max probability, based on those, the agent, or the bird, I will call it agent, will select one of these actions. So if we see here, going up should have a low probability, going down should have low probability, going left or right should have uh, a good probability. Okay, and one of those will have either one of those will have greater probability than the other one. So the network, given this image, the network should output probabilities, and it should output correct probabilities of the actions. Right, same thing as policy-based methods. Right. So how do we train this network then? How do we train the network to give out the correct probabilities given this image of the state? Is that uh, we collect many episodes. Okay, so this is the process. The bird or the agent will connect many episodes, try to reach here. Sometimes it will be successful. If it's successful, it will get a reward of that whole episode as one. And if it's not, if it strikes one of these vehicles, it will get a reward of -1, and the episode will terminate, as you can see here and here as well. So like this, the agent will collect many episodes. Okay, and then once it has collected many episodes, it will train the network. So how does the reinforce algorithm work? How can we use this reinforce algorithm to train this network? What is the specialty? So we have collected these episodes, many episodes, and so the reinforce algorithm will take, okay, for example, take one episode, take one time step, feed it, and you get probabilities. Now, as the name suggests, reinforce is going to increase the probability of the actions which have high probability already, and it will decrease the probabilities of the action which have low probability. So it's going to reinforce good actions and discourage bad actions. So after training, uh, after running the through one iteration of the reinforce, you might get this result. So now the probability of taking action left has been increased to 0.6. That's it. That's all what uh, reinforce means. In one line, it means increase the good probabilities and decrease the bad probabilities. That's it. Increase the actions, increase the probabilities for the actions that are good, decrease the probabilities for the actions that are bad. Now this is a good episode. What happens in a bad episode? So -1, -1. Same. And by the way, this is done at each time step. Okay. So this is just one time step that is shown. The probabilities of actions will be improved after each time step. So if the agent strikes one of the vehicles, uh, and if the agent strikes one of the vehicles, so this is the final outcome of the episode. So that means uh, what we are saying is that at each time step, the agent made some bad choices. So we need to reduce the probability of the choices made. That's the whole point here. Same goes for last one. So now, since it won and it got a good reward, the algorithm tells, while training, the algorithm tells the agent to increase the probability of all the actions that were taken at each time step, because eventually it resulted into a good outcome. So you should increase the probabilities of all the actions that were taken at each time step. Similarly here, it will decrease the probability of the actions taken at each time step. Now you feed this uh, this state, one state, and it gives out probability up. So point 3 was selected. So that means point 3 eventually led to a bad outcome. So it will, the algorithm or the agent or the network will decrease its probability and increase some other probability at random, but it will decrease this probability only. It will keep the other probabilities the same. It will decrease this and it will increase this probability. Okay, randomly. Uh, and then you move on to the next time step and do the same thing. Now you increase this and decrease this and kept this the same. Maybe in the next iteration, after finishing the episode, suppose again we ended up with a negative uh, reward, or you lost. That means left was also a bad action. So again, it will decrease probability of left as well and increase one of these two, and so on and so on. So that's the point of reinforced algorithm. Uh, Increase the probability of good actions if the total outcome was good, and decrease the probability of the actions taken at each time step if the total outcome, eventual outcome, was bad. So this is similar to classification problem. As many of you have had some hands-on experience on deep learning, other models of deep learning. Classification, suppose you have to classify an image between a cat and a dog. What classification problem does it? Suppose this is a dog. Okay, so this is an image, and you can see that it's a dog. So feeding this image to this network, the final layer will give out two probabilities, one for a cat and one for a dog. So that's its guess or estimation or prediction that this image is predicted as a cat with so and so probability and as a dog with so and so probability. If the network correctly assigns higher probability to the second node, which is represented by a dog, that means the network is doing good. So what the classification problem, the optimizer of this problem will do is increase this even more. So suppose if this was 0.6 and this was zero point 0.4, uh, and 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 it was closer to being the correct answer, uh, the classification problem will increase its probability to even more, like 0.7, 0.8, make this 0.7, 0.8 and reduce this even more. So that's what this reinforced algorithm is doing as well. It's very similar to classification problem. More details about this are in the lesson, and there is also a link to a blog in the lesson. So please take a look at that. Okay, so how does this reinforced algorithm work? What is the objective? How do we set up the problem? So first of all, we collect trajectories. Okay, now tau is represented by tau represents one trajectory. A0, A0, A0. So one time step, many time steps, end of episode. So one full episode is represented by tau. If it's a continuous task, so like a CartPole or pendulum task, you can assign maximum number of time steps that can be in one episode. So tau will represent those many time steps. R of tau is the total reward for that episode tau. Now here they haven't shown as the discounted reward, but when you implement this, you are most welcome to use gamma as the discounting factor for this. We have tau, we have R of tau to total reward for that episode, for that trajectory. And so our goal is to find weights theta, the weights theta of this network, find those optimal weights theta such that we have the maximum expected return. Okay, so reward is total return from an episode. Maximum expected return will be the average of many trajectories. Okay, also that on average the agent experiences trajectories with high return. That's it. So we have to change theta in such a way that our return every time for each trajectory is high. Okay, that's our goal. Again, it's the same. If you have watched the video on policy-based methods, change theta such that you get maximum expected return. Same thing here. So overall goal is the same, but the approach is bit improved. So let's see how we do it. So here we have an actual relation between theta and u. So that you can say that u is a function of theta. In policy-based methods, we were randomly changing theta, and we hoped that u will increase or decrease. The improvement in this policy gradient methods, which is a subset of policy-based methods, the improvement here is that we actually have an equation, a relation between u and the theta, the parameters of this network. And then we'll see how we use this relation. So again, find the weights that maximize the expected return, u. U is expected return, and u of theta is explained here. So let me explain this again. Very simple, no need to worry. So let's take a look. So R of tau is the return of that one trajectory. Okay, let's just take a look at this term. Forget the sum, sigma. Let's just take a look at this. So R of tau is the total reward or a total discounted reward of one trajectory. P of tau uh, of a theta is the probability of selecting that trajectory given theta. So given these network parameters, without changing network parameters, this theta, when we compute u of theta, before optimizing it, when we compute u of theta, use the same initial theta parameters. So given this version of theta, given this theta, what is the probability that I will have tau as the trajectory? Okay, so what is the probability that after this time step, I will have the other time step, and so on and so on, and that together, all those time steps make up tau. So, what is the probability of seeing tau, experiencing tau given theta? And why we want to the probability? Because we are using r of that tau. Okay, so because these r's will add up eventually, and they will uh, you know result into u. So we need to know what is the reward given this type of the tau, and what is the probability of experiencing this tau with current version of theta. Okay, and then we take weighted sum of all these rewards or given this trajectory. So it's going to be probability weighted sum of trajectories, rewards of the trajectories. That is your expected return. Very simple, no big deal. So here's the process. Here's the pseudocode. Use the policy pi theta to collect trajectories. So again, I said while collecting trajectories, and uh, and we are collecting trajectories so that we can collect rewards, and so that we can compute u of theta. So we use the same theta, and we collect trajectories, m trajectories, using the same network parameters. And so these are the trajectories, tau 1 to tau m, and each tau has this time steps. Okay, s0, a0, s1, a1 for tau 1, similarly for tau 2, etc. And so yeah, so these are the episodes collected so that we can collect rewards. So trajectories are collected here. What is the next step? Then we compute the gradient of expected return. So no need to worry about this. I will explain this soon. Um, uh, how So we collect trajectories so we can get this, and we combine this to get expected return, right? And in the lesson there is the derivation of how we derived the gradient of this expected return with respect to theta. That's what that term is. Delta theta u theta is the derivative of u, which is the function of theta, with respect to theta. That's delta theta uh, u theta. Okay, and okay, they're calling it j hat, g hat. Now, how did we get log of this all of a sudden, while whereas in previous slide we saw p? So please check out the lesson, and there is a derivation on this, and it's optional for you to know, but it's good to know, and it's very very interesting. If you have any questions about the derivation, you can ask me on Slack anytime. So uh, so what is this again? So R of tau is the total reward, discounted or not, total cumulative reward from the trajectory. Pi of theta is the probability of selecting action AT given ST, so one of these, and log of that. Okay, the log of the probabilities of selecting action given state times the total reward for that episode complete. Okay, cumulative reward. And we compute this, and then we take its gradient, and that will be our u of theta. Now here we have only shown for one episode. We do this for n number of episodes, and then there will be another term here, which is 1 over m. Tau goes from 1 to I to m, right? So this is the explanation. Simple. Okay, so once we get this, so this is nothing but d u theta d theta, derivative of u with respect to theta. Now, as compared to gradient descent, where we had to reduce the loss. So in gradient descent, this term will be L of theta, right? This term will be a loss. So we have a loss. We compute the derivative of loss with respect to theta, and we say that if I increase theta, if that is increasing my loss, that means it's a bad thing because I want to reduce the loss. So I will reduce the I will decrease my theta because increasing theta is increasing the loss. So I should decrease my theta. That's why there is this minus sign. Exactly opposite is expected return. We want to maximize the expected return. So if I increasing theta, if that is increasing my expected return, that means this du by d theta is going to be a positive. And so I will say that, okay, increase my theta because increasing theta is increasing my expected return. So I will increase the theta. So that will be my new theta. That's called gradient ascent, opposite of gradient descent. So yeah, so we do this and then so this is one iteration total, and then we do many loops. So here is the whole one loop. One loop is collect trajectories. So that means collect m episodes, right? If it's an episodic task, um, compute the expected return, and then compute the gradient, and then alter your theta, and again go to the same thing again, compute so many trajectories and the same thing again, and then change theta, just like gradient descent where this is minimized and this is loss instead of expected return. Just like that, same procedure but in opposite direction. We want to increase this, so this is expected return, and we add if this is positive, right? If this is negative, it will become negative automatically, and then it will reduce the theta. Okay, now let's take a look at the coding exercise. View. Yeah. So in the coding exercise, we implement this reinforce algorithm on the CartPole environment of CartPole environment by OpenAI Gym. So you see we also saw this CartPole environment in uh, continuing task example, right? Let me see if I can show you. Yeah, so this is the CartPole environment, right? So we are trying to move this block left or right, so that we can adjust this. We avoid this from falling, this pole from falling. That's the CartPole environment. Okay. So these are the state and action parameters. So one state is this four parameters, right? And it's a continuous state space, as you can see, and only two actions, left or right. So it's a discrete action space. So if 0 is the left and 1 is right, so if you push left, 0, 1 is right. Okay. Okay. So what this network will do? Okay, let's take a look at the code now. So in this example, in this code, in this implementation, I'm using the fully collected layers instead of convolutional layer. I could use convolutional layers too. Then I will have to use image as the input. But it's more convenient to just use fully connected layers because the input doesn't have to be an image in this case because there are just 4 parameters. 4 parameters make up one state. So no need to use CNNs here. No need to use even image. Okay, it's easier this way. So okay, so these are the libraries. Let me see if I can maximize. Okay, so these are so the reinforce on CartPole. So these are the libraries: NumPy, collection. I'm using deck. This will be used. This will be used to compute the mean, as you guys know already. This matplotlib will be used to plot the the expected return after training. Torch.nn for the network. This will be for the activation functions. Optim for optimizer, and this is new for you, categorical distribution. I will discuss this soon. These others are just for displaying the CartPole environments, so I skipped this for now. Okay, so first of all, the architecture of the network, architecture of the policy. We start our environment. We import an environment, CartPole seed 0, so that we can reproduce it. Okay, you know all this already. Okay, device, CUDA or CPU, the same syntax, whether it's going to be a CUDA or CPU. If it's available, if GPU is available, call it CUDA 0. Call device as CUDA 0, else call it CPU. Okay, so policy. So this is our network. First of all, it has these layers. Fully collected layer 1. So state size and hidden size. So if you see here, it's state size. State size is 4, and hidden size is 16. This is just 3, so ignore this, but it should be 16. And the action size, the final output layer, is going to be 2 nodes. So fully connected layer 1 will be this, and FC2 will be this, and this is just the input layer. Okay, forward, how will the states be inputted? So if X is a state, first it will go to FC1, so it will go through FC1, and then ReLU activation on it, and then that will be fed to the last layer. Okay, and then softmax activation on it, and that will give us the probabilities. And DIM is 1 because this is we say that perform softmax at the second dimension, because when you input the state to torch or anything to torch, when you input, it's going to be in this format, 1 by 4. It's not going to be 4 by 1. Okay, it's 1 by 4. So the output actions will also come out as 1 by 2. Actions will come out as 1 by 2. So I'm going to perform my softmax on the second dimension of my output layer. Okay. Okay. These are we are not calling this yet. We will call this later. I will just explain how this works. Now, the policy also has an act function. What does this act do? So it will take state as input. You know this line by now. We have used it for DQN, for in DQN in navigation project. It is to convert the state in NumPy array format from that to tensor. So we are converting the state in NumPy format to tensor, and we make it in a float type and unsqueeze 0. And I have discussed this before. So let me run this first. Okay, so you see here below observation space that I have printed. You see that this is 4, comma 1, right? But PyTorch takes input as 1 by 4. So that's why you add a singleton uh, dimension to its zero on its zero place. So unsqueeze adds a singleton dimension on zero place. So this 4 comma nothing, which we printed here, will now become 1 by 4, 1 comma 4. Okay. So singleton dimension has been added. And then we send it to device, whether it is GPU or CPU. So state, now we once it is a tensor in our format, we run it through the network and we get probabilities. Now the probability is going to be a tensor as well because it's been run through a network. Yeah. So this is the probability that we get. Now, and we are sending it to CPU because we don't want to use our GPU for simple calculations. This is completely optional. If you're doing a lot of computations, then this is useful to save GPU. You can just send it for simple calculations to CPU. We have computed probability. So probs is a probability tensor. Okay, it has a so it's a tensor of size 1 by 2. Okay, it will be a tensor of size 1 by 2. Now here we are using categorical probs. So what is this? So if you know about uniform distribution, it has equal probability, right? So categorical is a distribution of probabilities. So we are saying that create a distribution based on these probabilities. uh, they could be equal, but they might not be equal. So like uniform distribution has equal probabilities for each number, right? uh, if there are two numbers 0 and 1, and what that we have here, we have two action sizes 2, so we have two numbers 0 and 1. So in uniform distribution they will have equal probabilities 0.5 0.5, but in categorical prob it will have they will have probabilities based on this probabilities generated here, right? So we are doing nothing, we are just taking these probabilities and making it into a distribution so that we can sample our actions from this distribution. Not a big deal. We are just creating a distribution from this probabilities so that so we create this instance of this distribution from these probabilities that we got from our network. And when we sample, it's going to give out not the probabilities but 0 or 1. That's why it's called categorical distribution, because when you sample from it gives out 0 1, or if there are more than two classes, these are all classes, 0 and 1 is are like a classes. So more classes, suppose four classes, though it will give out 0 1 1 of 0 1 2 3 based on the probability, right? So we are doing nothing, we are just creating a distribution based on the probabilities so that we can sample 0 1 to 0 1 from this. In our case 0 and 1 of either 0 or 1 based on their probabilities. Okay, so action will either be 0 or 1, and this action here will be a tensor now, because this is a tensor, this is a PyTorch function, so it's going to be a tensor. So the sample from it is going to be a tensor. So action here is a tensor. So it could either be tensor 0 or tensor 1, tensor 0 or tensor 1 based on the probabilities. So I hope you got this. Then action.item will just give 0. We return only action item instead of action because this will be fed to the environment, OpenAI environment, which takes numpy arrays, numpy numbers. So action.item will just give 0 or 1, and dot log prop of actions will give out the actual probabilities that these actions had, 0 or 1 had, and the log of those probabilities. So log of this and this, it will be an array. It will be a tensor actually. Okay, so this will be just a number 0 or 1, and this will be a tensor of log of probabilities of both actions. Oh no, sorry, this will be a tensor of probability of only the action that was sampled. Yeah, tensor of log of, this will just give out log probability of the action that was sampled. Okay. So we haven't called them yet. So let's start our algorithm now. So we create an instance of our policy. We have optimizer, Adam optimizer here. Okay. So this is our function. We'll run 1000 episodes. Max steps in one episode will be 1000. Gamma is 1 here. You can use anything. You can use 0.9 to make it better. And we will print every 100 episodes. This is usual scores deck for print for taking average of last 100 episodes only, and you have similar steps, same steps. So for I in episode, we start one episode. Okay. Sorry, for I in episode in range 1 to n episodes plus 1. So it's going to be total 1000 episodes because we use plus 1. We make an empty list. So once we go inside this loop, we have started our first episode. Okay, so once the episode starts, we create an empty list of saved log probabilities and empty list of rewards. Okay, and then we get a random state from the environment dot reset. Usual steps, all these. And remember that these two will be discarded once the episode is over. So for next episode, there will be a new empty list of this and the rewards. So okay, so we get a state from the environment, and 14 range maxi. So we are limiting number of time steps in a episode in a trajectory, if you want to say, to 1000. Okay, policy dot act state. So we get action dot item. So we get either 0 or 1 here, and log probability of that action that was selected. So this again will be a just a number, and this will also be a number, but it will be a tensor. So remember that. Okay, and then I have this commented out, some codes commented out, because I wanted to see how they look like. That's how I knew that action is just a number and what log prob is. Okay, so I will go over this soon. So for now, ignore them. So once we get our action and log prob, we will save the log prob of this action that was selected into save log probs. So if you're getting this, why are we taking log prob and action is now take a look at this slide here. So look at this. We need log probability of action given state. So that's why we are collecting log probs. So this is just one trajectory. Okay, so for each time step, we are collecting log prob. So that's what we are doing here. And we want to get total reward for the trajectory. For this, we will have to sum up the reward per time step, right? So to get reward per time step, we need action. We need the action selected. This action will go into environment.step, and it will give out a reward. Okay, and the rest is the same. Okay, next state done, etc., etc. This is again for taking the mean of the rewards, usual steps. Okay, so now we are in the same episode now. Okay, so same episode, but we have broken from the episode. So we have run either 1000 steps, or the episode is over. Okay, and we have collected all the log probabilities for each time step, and we have collected all the reward for each time step in reward and saved log props. Now we will compute. We have to do two things. We have to compute R, right? And then we have to take a weighted sum of all the log props. Sorry, yeah, based on the log props, we have to take a weighted sum here. So it's going to be log probability of one time step times total reward plus log probability of second time step times total reward, and so on and so on. Okay, so we will first compute just this and sum them, and then we will take a gradient. So let's do it. So since we are discounting, this is a familiar step for discounting. We are creating an array of discounted numbers. uh, Here it's just one. If it was 0.9, so it would be 0.9 to the power 0, 0.9 to the power 1, 0.9 to the power 2, array. And then R will be uh, those each numbers here times the rewards that we have collected here. So this is like a discounted sum of cumulative rewards or cumulative discounted rewards, R, per episode. So this is just one episode, this first episode that's going on right now. Okay, now again, uh, I hope you have understood this, what we did. uh, for one episode we need to collect log probability of each action per time step, and reward at each time step. So the reward at each time step can be added up and discounted and added up to get this full reward for the whole episode. That's what we did here. And we have also collected this log probability per time step into log probs, saved log probs here, saved log probs. Okay, so how do we use them now? We create a policy loss empty list. Okay, now for log prob in saved log probs, so each log probability saved log probs, we will add minus of log prob times reward in this empty policy list. So why are we doing minus? First of all, sorry, let's do later. So why are we taking this product LP1 times R? Because we want to take, later on we will take a weighted sum of all those. So what we do is, we, for each time step, this log probability times the total cumulative reward, that's LP1 times R, comma, for next time step times R, same R, the R is same because the log probs are changing, and we are looping them from this saved log probs. Okay, and we use the minus sign because when we optimize this, we are doing gradient ascent as opposed to gradient descent. And we have used the same trick in DQN as well, if you guys remember. um, so when we use back propagation, the the optimizer tries to uh, minimize whatever we feed it. So if we provide minus of something, it will indirectly maximize it, right? That's the logic here. So we collect this minus LP, minus log prob of time step 1 times total discounted R, comma, blah blah blah, for all, into this policy loss empty list. Then we take sum of it. We take sum of all those here. So that's what is happening here. We put them together, and we took their sum, and these are all tensors. Okay, R is just a number, this is a tensor. So this new variable policy loss, it's not a list anymore, it's a sum of these elements here. So this is just a number. So this policy loss is log probability times R and sum of all those. So it's the log probability weighted sum of all the total R. So it's you get that it's LP1 times R, LP2 times R, minus of that, and sum of all those. So So policy loss is this total one, except for this. If you put this gradient theta outside, whatever is left, the total is policy loss, and you can call that as your u theta, your expected return. Okay, now one, and then we do the same steps for back propagation. First, zero grad, so we make all parameters zero, and then we run a back propagation, and then we optimize this. Okay, so that's how we are changing theta such that we can maximize expected return. That's how this step is working. Okay, and that's just one episode, and then we repeat this for all episodes. uh, yeah, yeah, for all these episodes, and we improve our theta such that we keep maximizing this policy loss after episode, and then when we run it, we should be able to maximize our expected return once. So it says if the score stakes or the totals of the score, average score of last 100 episode is more than 195, environment is stalled. So here it's stalled. So yeah, so that's how this is implemented. Very simple implementation. Network, we have this act. The only strange thing was this categorical is just a probability distribution, and from where you can sample categorical values, classification values, 0 1 if there are two classes, or 0 1 2 3 if there are more classes. That's the only new thing here. Rest is, and then we get a discounted sum of total R, and we take product of log probabilities, then take sum of those, and then maximize that. So this is our U here for this implementation. That's what we saw here. So, and I told you that you saw this print. So why I did this is because, so if you are looking at someone else's code, or if you are having an error while running your own code, print is the easiest way to uh, at least understand what the hell is going on, what's going on, why what's if it's someone else's code, and if you don't understand why that person did this, you can just use print and see what it outputs, so it clarifies things for you. Similarly, if you are writing your own code and if you get an error, print print out all those intermediate outputs and see if you are getting expected results, and you will be able to find what's going on. So even if you are not getting an error while executing your algorithm, but it doesn't work as expected, right? Even if it's working no error, but still it might not give you the results as you expected. So print is a very useful command. Print is a very useful step here, printing out everything. So if I have some 4 minutes now. So if I uncomment this, and so we can see what this what this output looks like, what is its type, and etc. and everything, whether they are a number or tensor. Instead of guessing, just print out the outputs, so it's easier. And I will reduce the number of episodes to 100, so I don't have to, or even 10. Okay, so I don't have to wait long. So I'm gonna save this, and I'm gonna save this and run it. Okay, so we have an output. So action in def act. So action is the function act in the policy. That's this one. And I printed action. So the m.sample that was sampled from this categorical distribution is a tensor, and in this case its value is 1. So as I typed out here, yeah, tensor 0, in this case it's tensor 1. And action.item that we are returning is just 1. So it's just returned the value 1. Okay, so even I was confused that what is this. First time when I saw this, I was confused. What is this doing, and why? What is this dot item? Why? And why are we using this? So I just printed this out, and it was clear. No big deal. And you get to learn from this even. Okay, now what is my next? So here I'm printing the action, what the action is, and what is this log probabilities. Again, I was confused what this, whether it is a tensor or a number or whatever it is, and what is the type of this log prob even. So action and log prob. So action is 1 again, and log prob is a tensor of log of the probability. Okay, so this is log of probability. This is not a probability at directly. This is the log of the probability with which I or the agent selected 1 as the action or sampled 1 as the action. What is the probability of that action? Not the sampling probability, but the actual probability of action, that was the actual log of the probability that was returned by the network. So this is the log of the probability of taking action 1 returned by the network, and it's in tensor form because it's a categorical. This is a tensor, it's a PyTorch function. Okay, another printout was here. So I put before cat because I'm concatenating here. So what was my policy loss? What was in the policy loss before? What was its length? So this will give me how many elements I have in this, whether it is a tensor or array, you will find out, and what is it. So even to find out whether it's a tensor or array, it's a tensor or array, I printed out, and after cat, and then what is the sum. So after this step, so before cat and after cat. So okay, since the episode is not over, it won't show now here yet. Yeah, so before cat, now 18. So this is the length. So this is the number of elements in that. So it looks like it's a tensor. So number of elements in this tensor are 18. So before cat, so the policy loss was a tensor and it had 18 elements. Even that was returned to me here. You can print out everything after cat and sum. Again, it's a tensor of all these tensor elements, sum of all these tensor elements, and it's a tensor as well. So that's, and you can also say that this episode had 18 time steps before it ended and started computing all these things. So yeah, if you see another episode, it had 11 time steps and it selected 0, and the log probability was this log of the probability that was outputted by the network was so and so. So just use print function, very very useful and very simple, and it gives you a lot of insights about what's happening while training. So that's it for, and then you can plot these things. I can plot this since it's only 10 episodes. Yeah, it's gonna look like that. But yeah, uh, you're most welcome to go over this again. If you have any questions, ask me. It looks very simple, no big deal. Only new thing was categorical, uh, and the trick is to use minus. Again, you know this trick from DQN. Again, any questions, ask me on Slack. I will get back to you as soon as possible. So I'm going to end this webinar now. So thank you very much.